Okay, so we briefly introduced this yesterday, okay, but I want to talk quite a bit about objects projected horizontally today, or just objects that are falling. So falling objects and objects projected horizontally, that's going to be our focus today. Okay, definition of a projectile is any object in unpowered flight. Okay, that's crucial. A plane is not a projectile. A plane has a motor. It's putting in energy to keep it flying. Okay, that's not a projectile, right? But anything that is in unpowered flight, anything you throw into the air, is a projectile, right? Missiles are not projectiles because missiles have rocket engines, so they're not a projectile. They're in powered flight, not unpowered flight. Okay, everyone all right with that idea? Okay, now projectiles, most of the ones we deal with, are going to have two dimensions to their motion, a horizontal dimension and a vertical dimension, right? The only projectile we'll deal with that doesn't have two dimensions is something that's simply dropped, okay? That only falls. And then the vertical dimension undergoes accelerated motion because the vertical dimension is affected by gravity. The horizontal dimension moves at a constant speed. Right? Because horizontally, there are no forces present to speed it up or to slow it down. Right? Because we're going to work in the perfect physical world where there's no friction or air resistance or anything like that. Okay, so we're kind of imagining we're working in the perfect physical world. Okay, everybody all right with that idea? Okay, so if an object is a projectile, it's going to be accelerating vertically and moving at a constant velocity horizontally. Right? So, let's go back to the thing I was showing you yesterday, okay, where you jump off the diving board, or platform. Sorry, we established it had to be a platform. Okay, so if you run off of this platform, we established, okay, that your arc will look exaggerated, something like that. Okay, now, initially, most of your motion is horizontally. Would you agree? Sorry, is horizontal, not horizontally. Is horizontal. Okay, but at the end, it's mostly vertical. Right? The reason for that is that initially, okay, what's your initial vertical velocity? If you run horizontally off the board, it's 0. Right? So initially, most of your motion is horizontal because you still have to accelerate vertically. And in that first second, you're going to go from from 0, you're going to fall about 4.5 meters, go from 0 to 9.81 meters per second. Okay? That's going to be the least amount that you fall. Now the next second, are you going to go even faster? And then the next second even faster. Okay? So as you fall, the speed at which you move vertically increases, but the speed at which you move horizontally doesn't. So if I look at those two dimensions separately, in my first second of vertical motion, I might only do that. Okay? In the next second of my vertical motion, I'm going to do that. And then the next second of my vertical motion, this, and then this, and then so on and so on. Okay, we'll just say that's where we encounter the bottom. Okay, do I travel further each second that I fall? Vertically, yes. Horizontally, I didn't do a very good job of this, but horizontally, those lines are all supposed to be the same distance. Okay, I go the same distance horizontally every second. Okay, so I travel at a constant velocity horizontally. Okay, I accelerate at 9.81 meters per second squared vertically. All right. Now we talked about the example yesterday of, if you are firing a gun and dropping a bullet at the same time, that they would hit the ground at the same time, okay, because they would fall the same distance. Of course, exempting the barrel, we would have to say drop it after it exits the barrel, and then that would be true. Okay. So if you want to hit a target, okay, if you're doing archery or if you're doing like shooting sports, okay? If my target is over here, do I aim at the target? Where do I aim? Yeah, way above it. Okay, depending on how far away it is, I aim above it. The further away it is, the farther above it I have to aim. Okay, because the bullet is going to fall as it travels horizontally. So if I correct for that, okay, then it'll do this. How many people have seen the movie Saving Private Ryan? Okay, in that movie, there's a scene where they have the enemy sniper is in the clock tower and he's got them pinned down. Okay, and the American sniper is talking about how he has to adjust his scope. He says it's 2 clicks. The guy's 2 clicks away. Even though he's only 800 yards, he says he's 2 clicks. He doesn't mean 2 kilometers. He means click the scope 2 clicks. Okay? By clicking the scope 2 clicks, what he does is he aims the scope down. So that in order to put his target in the crosshairs, he has to do what with the barrel? He has to lift it. So now his scope is pointed at the target, but the barrel isn't. Okay? What he has done is correct for the drop of the bullet. Okay? So he looks through the scope, he sees his target, he knows that the scope has already corrected for how far the bullet will drop, and the barrel is not aimed at the target, it's aimed above it. When he pulls the trigger, the bullet will do this. Whoop, wrong end of the thing. Okay, it'll do this. And it'll hit the target. Okay, because he's giving it a little extra distance to account for the drop. Okay, the longer the shot, the more you have to aim above the target. Okay. Anyone know what the longest sniper shot is? I think we talked about this, didn't we? Yeah. It's just under 4 kilometers. Okay, that's a long way. You got to aim a lot above your target for something like that. Okay, you also have to take into account wind. Wind is going to move the bullet horizontally from side to side. Okay, and you would also have to account for the fact that the earth will rotate under the bullet. So your target's going to move with the earth, and Coriolis effect comes into play. Okay, on a shot that far. Okay, it's crazy, but true. Okay. All right, making sense here? Okay. We're not going to deal with the projected at an angle projectiles till tomorrow. Okay. Today we're going to deal with just falling objects, okay, and projected horizontally ones. All right, remember I said we were going to look at like videos and we're going to pick them apart from a physics perspective? Okay, so I'm going to show you this video, and it's actually a commercial, and it's a commercial from like the late 90s, early 2000s, something like, I think it's late 90s. And it's a Lexus commercial. Okay? Lexus had this idea that they wanted to compete with European sports sedans. So they wanted to be in the same kind of market as BMW and Mercedes and Audi. They wanted to be a luxury sports sedan making company. So they went about and engineered what was considered to be a very high-end sports sedan at the time. Okay? The Lexus IS 350. Okay, and it was just a little 4-door sedan, but it had 300 horsepower, which at that time was a lot. Okay, for a 4-door sedan to have, that was a lot. And they said, okay, we got to market this in a way that is going to get people really, really excited about how fast our car is. How can we do that in a way that people have never seen? This is how marketing works, right? If they just show the car going fast, everyone's going to go, yeah, well, the Audi looks like that, the Mercedes looks like that, they all go fast, big deal. How can we really get people excited about this car? And somebody came up with the idea and they said, well, everyone is afraid of falling because they know gravity is fast. If you fall, you get going really fast. What if we tell them the car's faster than gravity? And people are like, well, we can't, I mean, there's a lot of, dishonesty in advertising, but we can't do that. Like that's an outright lie. People will see right through it. And the person's like, no, they won't. We're gonna fix it. They're like, you're gonna fix gravity? Good luck with that one. They're like, no, we're gonna set it up so that the car can be faster than gravity. We can do that as long as we set the distances right. So here's what they did. they shot a commercial where a car accelerated along an airport tarmac, and another identical car was dropped from a helicopter. And they raced to a single spot on the airport runway. Okay? They were equidistant from that spot when the commercial starts. Okay? So the car on the ground and the car being dropped from the helicopter are the same distance from the X. Okay? The car that's being dropped from the helicopter is just going to fall to the X. The one on the ground has got to race to it. Okay? Which one's going to win? What does your gut tell you? The falling car, right? Like that's what they were working on, is that our gut says falling things go fast. Okay, like it's instinctual. Okay, that's why there's a natural fear of heights. Falling hurts, falling makes you go fast. Okay, so they kind of played on that. So the car that's dropped, does it accelerate all the way to the ground? It doesn't. Because this is happening in the real world, where when you drop something, it eventually reaches its terminal velocity. Well, guys, another way they cheated this, they put weights in the trunk of the dropped car. Did you notice that the dropped car fell flat with its wheels facing down? If you drop a car, especially a front engine car from a helicopter, the first thing it will do is nose down. That is a very aerodynamic dimension for it to fall in. That's how cars are designed, so that the air going over them when you drive forwards, okay, is streamlined. They made that car fall flat, okay, which means its terminal velocity was as low as possible. In fact, lower than the top speed of the car when it's traveling on the ground under power. Okay? That car on the ground, the engine is driving it. Okay? It reaches its top speed, it's way faster than terminal velocity. Okay? Because constantly energy is being put into making it go. Right? This setup doesn't sound nearly impressive when you break it down and start thinking about what they did to make it look good. Okay? But they did a good job of making it look good. Right? But they did a lot of setup, okay, for that to work. Use that to answer this question. So I want to get you guys to draw this situation here. Okay, this is the movie is called Rebel Without a Cause, but I call it Rebel Without a Clue because doing what they did is stupid. Okay, so here's what we know in this situation. Okay, the car drives off the cliff at 25 meters per second, and it drives horizontally off the cliff. The cliff is 60 meters tall. Okay? What we want to figure out is figure out how far from the base of the cliff the car crashes into the ground. Okay, with any projectile motion question, we have to remember that the object, the projectile, is moving both horizontally at a constant velocity and vertically with accelerated motion. So what I want to do is separate those two parts and write down everything I know about them. Right? So I'm going to put all the vertical information here, and I'm going to put all the horizontal information here. Okay? So what do I know horizontally? Yep, I know that the speed of the car horizontally is 25 meters per second. Okay, because we said it's going to travel at a constant velocity horizontally. If it drives off the cliff at 25 meters per second, it is going to go 25 meters per second until it hits the ground horizontally. Okay. Vertically, what do I know?
It's accelerating at 9.81 meters per second squared.
Okay. Whoops. Okay, and I'm just going to say that that's down. Okay, is it okay for me to leave the 60 meters there as a piece of vertical information? As long as I put what on it?
Down.
Down, yep. Okay, what else do I know?
Initial velocity.
Right, I know the initial vertical velocity. What is it?
0.
Right. Because it drives horizontally off the cliff, it is not moving vertically at time 0. Okay, so last thing that we don't have on here is that we are looking for this. We're looking for the horizontal displacement of this object. Okay, so that goes over here. If it's moving at a constant velocity horizontally, am I going to use v equals d over t for my calculations horizontally? Is it okay to use v equals d over t for an object whose velocity doesn't change? Absolutely. That's the only formula really I can use, okay, for the horizontal part. So if I want to find d and I have v, what am I missing?
T.
Okay. Now, I also don't have t over here. But what's true about the time for the vertical and the time for the horizontal?
It's the same. It's happening at the same time.
They're happening at the same time for the same amount of time. Once that car crashes into the ground, it's not moving horizontally or vertically anymore. So, because time is scalar, I can use it for both the vertical and the horizontal parts, just like we could with the boat questions. I could use the time for going across and the time for going downstream. They were the same time, right? Can I find the time using my vertical information? Okay. Do I have a formula that has those 4 things in it? Which one?
D equals bit plus 1/2 at squared.
Exactly. Okay. I've got this formula here. You know, the one I told you you'd never have to use to solve for time unless, and VI is 0. So I can solve for the time using my vertical information and then pop the time over for my horizontal information because the time is the same. Okay? Everybody all right with that? So in any projectile motion problem, you're almost always going to have to find time because it's like the most useful piece of information because it's the only thing that can be applied to both the horizontal and the vertical dimensions. Okay? So if I'm plugging in my number, or sorry, manipulating for time here, I'm going to divide both sides by half of a and then square root to get t. Okay, so that's going to mean the square root of 60 meters divided by 1/2 times 9.81. I'm just going to make down positive. It doesn't change direction, so I could make them both negative, or I could just make them both positive. They're in the same direction. Okay, and that will give me my time. Okay, so I'm going to have the square root of 60 divided by half of 9.81, which is 4.905. I'm just going to cheat, guys. I just know that number. Okay, so that's 1/2 times 9.81. Okay, 3.5 seconds. Yeah, he screamed for a long time. It's been about 3.5 seconds. Okay? Long time to fall. Okay? 3.5 seconds. Okay, so I'm going to bring that over here. I'm going to keep all the decimals in my calculator. I'm not cheating by rounding off here. All right, so D will equal V times T. Take my 25 meters per second, because that's not going to change. Multiply that by 3.5 seconds. He's going to go pretty far. Okay, they're going to find the wreckage of that car 87 meters from the base of the cliff. Okay, so when I was drawing that diagram, okay, and showing this, I should have actually made this part longer. Okay, he was going so fast horizontally that he actually travels further horizontally than he does vertically. All right, how do we feel about that one? Okay. The horizontally projected projectile ones almost all work the same. Okay, like you've got to, there's a couple things you need to always remember for horizontal projectiles. This is the most important one. Okay, if an object is projected horizontally, person runs off a diving platform, car drives off a cliff, something like that. Okay, the initial vertical velocity is 0. If you don't remember that, it's going to be very hard to calculate anything because you won't have enough information. Okay? All right. So, in this question, okay, the bomber is moving at 200 meters per second. Okay? It drops the bomb, okay, and the bomb glides 1,800 meters horizontally before impacting the ground. What altitude was the bomber at when it dropped the bomb? Okay, so we had a 200 meter per second, so it was flying straight and level. Okay, flying straight and level when it dropped the bomb. Okay, now, if you are flying straight and level and you drop a bomb, is the bomb moving at the same speed as the plane? Yes. Okay, that's the challenge, okay, for a bombardier is when you drop the bomb, okay, the bomb is moving at the same speed as the plane. Should you keep flying straight and level after you drop the bomb? Where will you be when the bomb goes off? Right over top of it. Okay, so like when they drop nuclear bombs, like on Hiroshima and in movies, they would never fly straight and level after. You would always bank and fly off to the side, otherwise you would get caught up in the explosion. Okay, so we want to calculate the altitude that it was dropped from, or if you want me to say it a different way, the vertical distance it falls. All right, give you a few minutes, see if you can figure that one out. Okay. So, as we said, we want to break this up into kind of a vertical component and a horizontal component. Okay, what do they share? What's the one given that they share? Time. Okay, so I know that that's going to be in both and it's going to be the same number. All right, vertically speaking, I know this. Agreed? Right, they were flying straight and level when they dropped the bomb, so the bomb and Kong have an initial velocity of 0 meters per second. Okay, and then I would also know this. Okay, that it would be accelerating downwards at 9.81 meters per second squared. Right? From a horizontal perspective, I know two pieces of information. I know the horizontal velocity, 200 meters per second. Okay, and I know the horizontal distance, or displacement, 1,800 meters. Okay, I'm trying to find the height the bomber was flying at when it dropped the bomb, or the vertical displacement of Kong and the bomb. Okay, everybody with me there? So if I'm going to find the vertical displacement, I need at least one more piece of information vertically. Would you agree? Okay, but that other piece of information could be VF if I could find it, okay, or it could be time if I could find it. I don't see any way for me to get VF. Can I get time? Yeah, I can use the horizontal information this time to get the time. So it's not always going to be that you'll use the vertical to get time. Sometimes you use the horizontal to get time and go back the other way. All right, so time will equal D over V. So 1,800 meters, okay, divided by 200 meters per second should give me 9 seconds, yeah? All right, so now I can bring that over here. Okay, the time's going to be 9 seconds. D will equal VI times T plus 1/2 AT squared. All right, so that'll be, that's 0. So 1/2 times 9.81 times 9 squared. Okay. I think we only, what we have, three significant digits in that. So 397 meters. Okay, would be the altitude of the bomber. Okay, which makes sense. They were like, you know, down in a canyon. Okay, they'd be pretty low. Yep. Okay, making sense? There's actually quite a bit of like really applicable stuff with projectile motion, okay? Especially if you start getting into like how sports work, especially things like baseball, football, and golf, okay, where you know your whole idea is projecting the ball, okay, somewhere else. Okay. All right, any other questions on that one? Okay. So Thelma and Louise waste that perfectly good Corvette. Or, sorry, was it Corvette or Thunderbird? I don't remember. Anyway, that nice car, okay, off the cliff, okay, they go plummeting down to the bottom of the thing, okay. So here's what I want you to find in this one. The cliff is 200 meters high. The acceleration due to gravity is 9.81 meters per second squared because this occurs on Earth, okay. And of course they drove horizontally off the cliff. You can see that. They did a really good job of driving right horizontally off that cliff. Okay, so VI is 0. The car's wreckage is located 165 meters horizontally from the base of the cliff. How fast did they drive off the cliff? How fast was the car going when they drove it off the cliff? That's what I want you to calculate here. Okay, so if we're, again, writing down our givens here, these are the vertical ones, okay, so they're already kind of organized together, right? Our horizontal givens, okay, would be the distance, 165 meters, and we're looking for V, right? So what are we missing? Time. All right, so okay, in almost every projectile motion question, time is going to be something you're going to have to find. If a projectile motion question gives you time, there's probably some other little trick that's going to take time away from you, okay, make it take a long time, okay, if that happens. So I'm going to solve for time using my vertical information, using that same formula. We've used it every time, okay, so far for this, okay. VI is 0, so I'm solving for that. That'll be the square root of D over half of A equals T, okay, so that'll be the square root of 200 meters divided by 1/2 times 9.81. Okay, so it's going to take 6.385 seconds for that car to crash into the bottom of the Grand Canyon because it's deep. Okay, so now that we've got that, okay, so 6.4 seconds or whatever it was there. Okay, whoops, that's the time. Now I can find V. V is just going to be D over T, 165 meters in 6.4 seconds. Okay, so they drove off the cliff at, what do we have, 3 sig digs? Yeah, so 25.8 meters per second. Okay, everybody all right with how those work? Okay, all projectile motion questions essentially break down to I've got to find one thing in the vertical or horizontal so I can use it in the other.
Is this gonna be on the quiz Friday?
No, Friday's quiz will just be acceleration.
Okay.
All right. Okay, one other one I wanted to show you here. Remember I told you the bullet fired, bullet dropped? Okay, so I got the actual. Now, the thing with that is that they because it's Mythbusters for the impatient, okay, is that they didn't show you how they figured out where to put the dropped bullet. Okay, if you didn't notice, the bullet that was dropped actually hits the paper in the same spot as the bullet that was fired. Okay, they had to do some calculating there that they had to use that they knew the muzzle velocity of the gun, so they knew basically how far that bullet would go in the time it would take the bullet to fall. Okay, so they knew where to set that so that they would hit the paper in the same spot. They edited that out, excuse me, for the sake of expediency on that one. Okay, all right, are these horizontally projected projectiles making sense? Okay. Now, what was the damn? Okay, see if you can do that one. We'll quit after that one. Okay, how high must a cliff be so that a person who runs off the cliff at 8 meters per second would hit the water 15 meters from the base of the cliff? It's water, nobody dies here. Okay, it's a splash, it's fun.